Okay, if there are no doubts, then we can start the lecture. I hope my whiteboard is visible properly.
Yes, sir, it is visible.
Now, today's agenda is interesting. So what we have seen already in our lecture, suppose there is a main program and this main program, if it calls a fork function or make a system call fork, then what we have discussed that another process will be control is shifted to kernel, and in kernel fork function is defined, and now when fork function is about to return, this fork function returns at two places, because during the execution of fork function a similar process, child process, have been created. So after the execution of fork function returns in parent the PID of child, and in child it return 0. There's any doubt in this? Abhigyan, any doubt here? This we have already
No,
discussed.
sir. Yes, sir.
Okay. Now the issue here is this is a very spatial function. And if you think carefully, it is doing a lot of work. Before the execution of this function system call finishes, another process is created, which is replica of parent. And if it is a replica of parent, then the code part of the process would also be copied. The code segment means this child process would also be having this line. So before the execution of fork, child process is not there. And in a normal function call, if suppose this is a normal function call or a system call, this should return after this line. But during the execution of fork, a new process is created, which is also a replica. Now fork has to return at two places. Now this is interesting. Listen to the statements carefully. When fork has started execution, there was no child. During the execution of fork, the child is created, which is exact replica of the parent. Means this function call would also be there in the child process. The system call will also be there in the child process. Now both in parent and child process, this fork has to return just after this line, just after this line. So when the function execution started, there was no existence of the child process. When it finishes, it has to return at two places. My question is, how can we write a C function like this in this situation? Anybody? Are you getting the spirit of the problem? The actual point which I want to put forward? Anybody can answer or try to answer. Yeah, Aman Singh.
Sir.
You got the problem?
Yes, sir. Sir, I was thinking, means I have one question related to that. Means you have said that in the child process, it will be exactly the replica of the parent process.
Mm-hmm.
So inside it, also the fork process will be called.
Mm-hmm.
Sir, then how that fork process calling will get started? Means inside the child process, we will be again calling that fork process.
No, no, no. Exact replica means parent has already called fork and parent's program counter is already incremented. So what is the return address? Return address would be pushed on stack, which is the next line after fork. And return
Okay,
address
sir.
and everything will also be copied here. Are you getting the point? Remember
Yes, sir.
the trap frame and context structure. Okay?
Yes.
Because we have studied interrupt handling. So child will not execute fork again. Because in child also you have to return after fork. Got the point?
Yes, sir.
Now answer. Anybody else want to answer? Isn't it interesting? Abhigyan?
Yes, sir.
You are fifth semester computer science, IT. Uh, you guys are good programmers. Think of how we can do this thing. And fork is a C function. How a function can return two values? Anybody else can answer.
So like whenever we want to return more than one like value, we generally use pointers.
Here the case is different. Who's that chap? Lovedeep. Huh. Am I pronouncing your name correctly?
Yes, sir, it's
Yeah.
correct.
So here the situation is different. Yes, I know that you can transfer the return the address of some structure or return the address of array where the return values can. But can you return at two different places? This is another address space.
Sir, maybe it's like two things are being returned, but by different processes, but not like so. Not a single process is returning two values.
Not a single process is returned,
So,
but
like,
you are
so
in a parent process, and parent process has called fork. So only the mode has been switched, as I told you. Then when you call a system call, a mode will be switched, but you are still in that same process. Kernel is executing on the behalf of parent process. So fork, and forget about everything. There would be only one fork instance which is running. Anybody else who can try?
Sir, I think why to return value if we can change the PCB of both of the processes.
Why to return value? But function
So
must return
like,
some value, no?
so we can change the PCB value of both of the processes.
PCB what? PCB what value?
Means the process control block contains the instance of the process, so we can like
Come on, go on.
so we can the variable that is PID, we can change that for both of the processes. So whenever the
So you mean to say that fork is not returning any value?
no sir, I don't think so. So how can it return at two different places?
That's what is the agenda of today's lecture. I think now you got the spirit of the problem. Okay? हर एक समस्या की एक आत्मा होती है, ठीक है? वो आत्मा से साक्षात्कार हो गया है आपका, शुद्ध हिंदी में। ब्रजेंद्र ठीक है?
यस सर दैट इज गुड। अब सर आ जाएगा इनको समझ में।
अब समझ में आ जाएगा, हाँ। नाउ लेट्स सी we have already seen interrupt handling in detail, and as I told you that system calls are also handled like interrupt. So when you are writing a C program and want to use a system call directly, so in user space C library of x86, there is a file user.h where these system calls are defined as function calls. So you can use those system calls like fork, exec and all. And later on, uses.s converts this user space library function call into actual system call. And as I told you, at this place, the int instruction, interrupt instruction will be invoked. CPU interrupt instruction will be invoked by uses.s with a suitable argument. And what was that argument? We have seen in the lab class, that is 64. For all the system calls, there is only one argument. And that will indicate that a trap is due to a system call. Right now, we don't know what system call it is. Main trap handling function. Let me open the code first of all. Just a minute. I forgot to open the code. Just a minute. Give me 1 second. Okay. So the main trap handling function, which is at line number 3350, will look at the argument passed to the int. Fine. So let's see what is there at line number 3350. So it's a, let me maximize it a bit. So at line number 3350, there is a trap function. So it will be, and the argument to this trap, main trap function, is the trap frame. So as we have seen in interrupt handling, so we'll see that, okay, trap number is t underscore syscall, and it suggests that now we need to do the system call handling. That's what is mentioned here. Now it will call the common system call processing function syscall in line number 3624. Okay, so in line number 3624, so it will call a syscall function. If it is a system call, the syscall function will be invoked, and where it is defined, it is defined in 3624. So this is syscall. Now what is happening, what you are doing, syscall function, and depending upon the number of the syscall which is already pushed in EAX register, fine, when the system call was already pushed in EAX register, we'll see that number, and depending upon the system call number, we'll be executing whether it is sysfork or sysexit or syswait or syskill or any other system call. In usage.s system call number, when this usage.s was executing, the system call number is pushed into EAX register. The common syscall function looks at this syscall number and invokes the specific function corresponding to the number or system call. So the whole path is same. The way you do the interrupt handling in system call, there is only one argument for all the system calls, and there is one step extra. So it will be doing all trap function, and that all trap function will be calling the trap function. In trap function, you will see the number. Okay, it is 64. It is for system call, and if it is a system call, then you are calling a common syscall function. And then you are observing the EAX register, getting the number of system call, and accordingly you are calling the required system call. Now, system call fork, because we are discussing here system call fork. So in XV6, we are having these process states: unused, embryo means new, it is just created; sleeping, ready to run, runnable; running, it's on the CPU; and zombie, it is killed, but its remnant have not been collected by the parent. Unused, embryo, sleeping, runnable, running, and zombie. So when a process call fork, generic trap handling function calls a specific system call fork function line number 2554. Fork function is defined in line number 2554. And please, those who are sleeping should wake up. So let's see the fork function at 2554. So this is the fork function. Now what it is doing, it is first of all declaring two integer I and PID, and then declaring a structure pointer of type proc. Remember proc structure? Proc structure corresponds to PCB. Remember when we were doing the trap handling, the proc structure. So what we have done, we have created a new structure variable of struct proc type. Now what we are going to do, we'll call the alloc proc function. If you are trying to create a new process, the first step is to create its PCB, process control block. And what is process control block? If you remember, we can go back. This is proc data structure, which corresponds to PCB. Remember struct proc, where there were kernel stack, trap frame, context, and all that. So first of all, if a new process is going to be created, the first step is to create its PCB, and PCB corresponds to proc structure. So first of all, you need to create a processes PCB, and that's what is getting done. Fork calls the alloc proc function. Fork calls the alloc proc function. Now, what this alloc proc is trying to do, alloc proc, because you know different process states are embryo, sleeping, runnable, running, zombie, and there is an unused. Unused means there is a proc structure which is unused, just created but unused. And that unused proc structure will be allocated to this new process which is getting created. Alloc proc allocates a new unused struct proc data structure and initializes it. Lines number 2460 to 2465. So let's go to 2460. 2460. Now here, alloc proc, this is alloc proc function. This is struct proc pointer, another pointer, structure stack pointer. Now, as I told you at that time also, this is most important because the list of PCB are there in P table. Remember P table? P table is an array of pointers of PCB. Array of proc structures. So you want to access this P table. So you do the locking, acquire the lock, and you just run a for loop up to the number of proc structures which are there. Keep on increasing the pointer. And as and when you found an unused proc structure, you go to found. And here you initialize the proc structure, which is just allocated. What you're doing, you are doing P state as embryo, PID is whatever is the next PID. There is a variable next PID which is incremented. And then you release here also. Otherwise, if you don't found, release it. And if you do not found any unused structure, what will happen in fork? Fork is defined in line number 2554. If you are not able to find any unused structure, then you go to 2554 and you can see if you are not able to get any unused structure, then return -1 means a new process cannot be created. And then you get a P error in fork function system call when you call it on your main program in high level language. So this is how whole process is. When high level language calls fork, fork is a library function which is converted into system call by uses.s. During the system call, uses.s pushes the system call number to EAX register. Now the all trap function will be called. What all trap does, you have seen. All trap calls the main trap function. In main trap function, you see the argument which is pushed to which was argument of int instruction. You know it's a system call. You go to the syscall function. In syscall function, you read the EX register, which gets you system call number. Using system call number, you get to know it is a fork function. You go to the fork function. In fork function, you are now trying to allocate the proc structure. If proc structure is not able to get allocated, you return -1, and later on this -1 will result in P error when you are trying to call the fork function in the main C program, in your user space C program. Otherwise, if it is successful, then you will initialize that proc structure in line 2460 as we have seen in line number 2460. Acquire state is embryo, PID is given. Fine. This initialization is getting done in our found. So let's see what other things. It also allocates a new kernel stack for the process, line number 2473. Because now a new process is getting created, so you need to give a kernel stack pointer also. That would be a part of trap frame of this new process. So you also allocate kernel stack kalloc. Fine. So we'll come back to these things later on when we do the memory thing. I'll be telling you how this kalloc and everything. Right now you can just see that you are trying to create a kernel stack of new child process also. On kernel stack of a new process, alloc proc pushes various things, beginning with the trap frame. कई चीज push करता है वो. On kernel stack of new process, alloc proc pushes various things beginning with the trap frame. And once alloc proc returns, the fork function copies the parent's trap frame onto the child trap frame. How? Let's see, line number 2572. When alloc proc will return this pointer, and in fork we have called alloc proc. So what is that line number? That line number was 2572. 2572. So what you are doing? जो trap frame अभी currently है is of the parent process would be copied into new process, and that's why this new process pointer we have created proc type structure. Proc type structure, this np, and when you call alloc proc will return a pointer to the new proc structure. And now what we are trying to do, we are trying to copy the existing trap frame of the parent proc trap frame to new process trap frame. So whatever is the trap frame right now would be copied to the new process trap frame. Now both child and parent have the same user context stored at the top of the stack. So what is happening? Now come back to whiteboard. When this fork was executing, what it has done, it has allocated the PCB, new PCB. Fine. Allocated the PCB of a new process, and then in that PCB kernel stack is allocated, and on kernel stack trap frame is pushed, and on trap frame what is the parent trap frame is copied. Just a minute. Okay, So parent trap frame is copied to the trap frame of child. Now this trap frame also has the return value. So when you call trap ret, remember trap ret? So whatever you have pushed on the stack would be restored when you call trap ret. In both processes, you'll get the same return address and you'll be returning to the same place in both processes. So now both child and parent have the same user context stored at the top of the stack, and during trap ret, both return to same point in user program right after the fork system call. Any doubts here to anybody up till now? Abhigyan?
No, sir.
Clear?
Yes.
Okay. Now there is a jugaad, because it's not any, it's a jugaad that how child fork return 0 in child process. And jugaad is, do you know this thing, Aman? It is in our Oxford dictionary also, this word.
Yes,
You know
I
this
know
thing?
this word.
No, but it is in Oxford dictionary. You know this thing or not?
Sir, I was not knowing this fact.
This is there. So the world's most trusted English dictionary, Oxford, has officially accepted the word jugaad in their latest update. Jugaad means a flexible approach to solve a problem that uses limited resources in an innovative way. So what Falk has done, and not Falk, what Cunningham and Ritchie has done a very intelligent jugaad. So the question was how fork returns two values, that too in two different processes. Fork function fills 0 in the EAX register in the child's trap frame. और एक बार पीछे ले जा रहे हैं आपको, जब इनिशियलाइज किया था मैंने ये लेक्चर, तो मैंने कुछ बताया था आपको. These registers I have told you of x86. Fine. And then what I have told you, if you remember, just for you, callee places the return value of the function in EAX register before returning to the caller. Callee means the function which is called places the return value of the function in EAX register by convention before returning to the caller. Now what is happening? ध्यान से सुनिएगा. What is happening? When fork was executing, a new child process is created. I have told you a new proc structure is allocated. New PCB is there. New trap frame is there. Parent trap frame is copied into the new trap frame. Fine. So there is the existence of new process which is having a state as embryo, and PID is given. Everything is given. So how fork return two values? Now what fork function is doing? It will return to, if you see our whiteboard, fork will return to the parent process only, because it has been called from a parent process. If you see carefully, fork is called in main function, and fork will return normally to the parent function. So the fork call will return to the parent function. That is okay, as if it's another system call. But what is a specialty in this fork, that during the execution of fork, a new process is created. And exact same process is created where also there is a line fork. int p equal to fork. Now fork will return to parent or the function which has actually called it, main function. But right now what is happening during the execution of fork, there are two trap frames, parent trap frame and child trap frame. There are two trap frames. Obviously the child trap frame is copy of the parent trap frame. That's why you have return address and everything same. But what deliberately you are doing, that in child trap frame, you are deliberately writing EAX equal to 0. And parent trap frame, whatever would be the return value would be written by fork. That's a normal function call what it is doing. Okay, so let's see what is happening. Child trap frame line number 2575. Let's see the line number 2575. It is here only. Here, the new process TF EAX is 0. Okay. So 0 is pushed into the EAX register, which will call the child to return with value, because child hasn't called fork, but because it is there in its code and the return address is also there. So you have to have a return value also, and you have pushed the 0 in the EAX register. So you have actually kind of emulated returning value of 0 in the child process. And in parent fork function, in parent fork function returns with the PID of child, line number 2591. We can see the line number 2591. Here you can see return PID. Simple. Because parent has called fork. At the end of the day, you will be returning PID. And PID is what? Whatever this PID is copied into the PID. New process PID will be copied into the PID variable, and PID is this parent process variable, fine, and this will be returned. Child PID will be returned to the parent process who has called fork. So in this way, fork emulates returning of 0 in child process. The alloc proc function also pushes on stack the address of the trap ret. Address of the trap ret, line number 2486, and the context structure. एकदम ध्यान से सुनिए, ये अब एक्स्ट्रा हो रहा है इंटरप्ट हैंडलिंग के अलावा, because in interrupt handling we were only dealing with the trap frame. Remember, we were only dealing with the trap frame, but now we are dealing with the context structure also, which is there in the stack. So what you are doing, the alloc proc function also pushes on stack the address of the trap ret and the context structure. So let's see the what is happening. 2486 alloc proc function 2486. Okay, just a minute. So what you are pushing in alloc proc function, this alloc proc function in line number 2486, it is pushing the address of the trap ret also. किस process में? In child kernel stack, because alloc proc is doing what? Is making the PCB of child. So in PCB of child, in child stack, it is also pushing the address of trap ret. Then what is pushing? It is pushing the context. context of the process, which is same as the parent process. So it is alloc starts at the bottom of the kernel stack in the beginning, line number 2477, 2477. यहाँ से pushing शुरू हुई, stack pointer, kernel stack, keep on pushing, trap frame push किया, then we are pushing the address of trap ret, and then we are pushing the pointer to the context structure. This is what we have pushed into the child kernel stack. So in child kernel stack, it would be trap frame, which is already there because it's an interrupt call. First interrupt will be handled, and interrupt tells you that it's a system call. In system call fork, alloc proc is doing what? Pushing the address of trap ret and pushing the context. And this context is same as the parent context. Now what is context? If you remember, we have discussed this initially when we were handling the interrupt. In proc structure, there are 3 pointers: kernel stack, trap frame, and context. Context is needed whenever you want to switch to a new process. When kernel switches context from one process in kernel mode to another during a context switch. These are two different structures I told you, and need to store different set of register in these two situations. So what alloc proc is doing in addition to all these, it is pushing the address of trap ret and context. And in context, what you are pushing, that's the next interesting thing. In context, what you are pushing, first of all, let's see why context structure of child on a kernel stack. Please be with me. Please be with me. New process just created. What is a context? I told you, when a process executes on CPU, it develops a context, registers and all, and whatever is doing with the CPU and everywhere, it develops a context. So what is currently happening in the CPU when a process is executing? A new process is just created, has not run till now. Then why context is needed? Why we need a context? That's the major question. अभी तो रन ही नहीं हुआ ये नया प्रोसेस, अभी तो जस्ट बना है, फिर इसका कॉन्टेक्स्ट क्यों चाहिए? हाँ, प्रोसेस कोई रन होता है, कॉन्टेक्स्ट हम मेंटेन करते हैं, because whenever process switches off, we need to save this context in the context structure. New process तो अभी just बना है. Why? Just see. Why context structure of child on kernel stack? Actually, it is needed when a running process is switched by scheduler or leaves the CPU for any other reason. So that when process resumes, context can be restored. ये तो जब process run कर रही होती है तब हम context save करते रहते हैं. So that whenever we want to switch, we will save the context so that next time when we resume, the process resumes, it can start from where it has left. But for a newborn process, it is strange that context structure is getting pushed on a stack, because it is never switched out from CPU, and actually it is going to run first time. Why we require this context structure of child on kernel stack? This is another jugaad. What alloc proc is trying to do is trying to create an artificial context on the kernel stack of the child process. Just to make this process appear like ये कभी पहले रन कर रही थी और कॉन्टेक्स्ट स्विच आउट हो गई है. अब सीपीयू शेड्यूलर जो शेड्यूल करता है सभी प्रोसेसेस को, वो क्या समझेगा, यार ये कोई पुरानी प्रोसेस है, इसका कॉन्टेक्स्ट भी बना हुआ है, ये स्विच आउट हो गई होगी, तो वो इस नई प्रोसेस को भी शेड्यूल करने के स्टेट में आ जाएगा. Now CPU scheduler can schedule it like any other process that is context switched out in past. This jugaad enables the system that once a new process is created and added to the list of active process, the CPU scheduler can treat it like any other process. कुछ special treatment नहीं है, जैसे बाकी सब रेडी टू रन है, रनेबल स्टेट में है, एम्ब्रॉय से रनेबल. जब सब काम पूरा हो जाएगा तो जो पीआईडी जो स्टेट हमने एम्ब्रॉय रखी थी उसको रनेबल कर देंगे, तो ये भी रनेबल हो गई. इसका भी कॉन्टेक्स्ट बना दिया आर्टिफिशियल, और कॉन्टेक्स्ट में रखा क्या है, ये सब रख दिया, ट्रैप फ्रेम डाला, ट्रैप रेट डाला, कॉन्टेक्स्ट बनाया एक आर्टिफिशियल. बट उसके कॉन्टेक्स्ट का जो प्रोग्राम काउंटर है उसमें फॉरकरेट एक और फंक्शन है, उसका एड्रेस दे दिया फॉरकरेट. We'll be seeing what is forkret. ये चाइल्ड के स्टैक में कर रहे हैं अपन. ये अपन कहां कर रहे हैं, चाइल्ड के स्टैक में. Now let's see. The EIP is set to point to a piece of code called forkret, as I told you. Means child process starts execution from forkret when it returns to the main function. The forkret function, which is defined in line number 2783, does a few things and returns. Let's see how the EIP is set in line number 2491. In line number 2491, P context EIP is set to the address of forkret. प्रोग्राम काउंटर चाइल्ड प्रोसेस का forkret में डाल दिया. ठीक, चाइल्ड प्रोसेस का forkret में प्रोग्राम काउंटर डाल दिया. Now what will happen when child process will execute? Scheduler will schedule it. It starts execution क्योंकि उसका प्रोग्राम काउंटर हमने forkret के एड्रेस पे सेट किया है. Start execution from function forkret, which is at line number 2783. Line number 2783. Is a forkret. ये कुछ करता है. We'll be seeing that. When forkret returns, the process executes. Forkret function does few things and returns. Forkret कहां रिटर्न कर रहा है? Returns to caller. It returns to caller. Actually, it returns to trap rate. Trap rate क्यों करेगा? कर्नल स्टैक में डाला है रिटर्न एड्रेस. Top of the stack, trap rate. तो क्या किया, EIP सेट किया forkret पे. प्रोसेस रिटर्न होगी जब चाइल्ड प्रोसेस फॉक से रिटर्न होगा तो forkret एग्जीक्यूट करेगा. forkret एक्चुअली कुछ नहीं करता है, कुछ काम करता है. When forkret returns, the process executes trap rate because return address of trap rate is now present at the top of the stack. And we know that address of the top of the stack is used to used as a return address when returning from a function call. जुगाड़ देख रहे हैं आप लोग कितना है इसमें? ध्यान से समझिए, फिर से बता रहा हूं. चाइल्ड प्रोसेस में भी फॉक कॉल हुआ है. चाइल्ड प्रोसेस को कहीं पे रिटर्न करना है, बट अपन ने क्या किया, चाइल्ड प्रोसेस के प्रोग्राम काउंटर को चेंज कर दिया. किधर चेंज किया? फॉक रेट पे, एक फंक्शन कॉल पे. अब ये फंक्शन चलने लगा. अब बाकी सब चीजें हट गई चाइल्ड प्रोसेस में, फंक्शन कॉल हो गया एक फॉक रेट. अब ये फॉक रेट भाई रिटर्न भी करेगा. कहां रिटर्न करेगा? कोई फंक्शन रिटर्न करे, कहां रिटर्न करता है? रिटर्न एड्रेस कहां होता है? टॉप ऑफ द स्टैक पे. टॉप ऑफ द स्टैक पे हम पहले ही क्या डाल के रखे हुए हैं? ट्रैप रेट का एड्रेस. तो एक्चुअली क्या कॉल हो जाएगा? ट्रैप रेट कॉल हो जाएगा. एंड व्हाट ट्रैप रेट डज, रिमेंबर, जो ऑल ट्रैप फंक्शन पुश किया है उसको सबको रिस्टोर करेगा इन द चाइल्ड प्रोसेस. Address of the top of the stack is used as a return address when returning from a function call. Newly created process, when it is scheduled on the CPU for the first time, simply behaves as if it is returning from a, ये कोई interrupted process है, वहीं से रिटर्न कर रही है क्योंकि ट्रैप रेट चला रही है. तो न्यूली क्रिएटेड प्रोसेस ऐसे बिहेव होगी जैसे कोई इंटरप्टेड प्रोसेस. इसका कॉन्टेक्स्ट स्ट्रक्चर भी है, इसका ट्रैप फ्रेम भी है, इसका सब कुछ है. ठीक है. इट इज जस्ट लाइक somebody has interrupted this process and now it is returning from the trap. It is just like the normal interrupt handling. Interrupt handling में क्या होता था? ट्रैप. After handling the trap suitably, the trap function returns to line 3272 from where it was invoked. After trap returns is execute the logic at trap rate. Normal interrupt handling में भी trap rate call होता था. Trap rate क्या क्या करेगा? जो जो push हुआ है वो pop करेगा. I rate का भी वो जो जो interrupt ने int instruction ने push किया था वो सब होगा और trap handling complete होगी. ये normal interrupt handling में होता था. So we wanted to have the same thing in new process creation because this is ultimately this is a function call. This is a system call. So system call, other should this fork system call should also behave as another system call, and another system call is nothing but an interrupt handling. So we wanted to make this fork system call also look like the interrupt handling, and that's why we have done all these things. Fine. Final words, we have seen that the trap rate function pops the trap frame from the kernel stack, restores the user space concept, returns the process to user mode again. The child's trap frame is exact copy of the parent's trap frame. And the parent's trap frame stores the user space context of the process that stopped execution at the fork system call. And ultimately, when child process resumes, it returns the exact same instruction after the fork system call, much like the parent, with only a different return value. How? We have seen that, remember, the EAX register. अब बताइए किसी को अगर ना समझ में आया हो तो. अभिज्ञान.
आ गया सर.
ब्रजेंद्र.
यस सर, बहुत बढ़िया बताया सर आपने.
सब समझ में आ गया?
यस सर. इसमें मतलब बाकी सिस्टम कॉल्स में क्या होता है कि ट्रैप रेट एक ही बार एग्जीक्यूट होता है, फोर्क में दो होगा, दोनों में
होगा. और जो नई में होगा वो पहले फॉक रेट चलाना जरूरी है.
हाँ, फॉक रेट
फॉकरेट 2 लाइन का फंक्शन है केवल, वो खाली ट्रैफरेट में उसको भेजना है, रिडायरेक्शन करना है, इसलिए फ्रॉकरेट नाम का एक डमी फंक्शन है वो फॉकरेट, जिससे कि हम रिटर्न कर पाए ट्रैफरेट, और ट्रैफरेट को ऑलरेडी पुश किया हुआ एड्रेस उसका स्टैक में।
यस सर।
ठीक है, तो इसको जरा एक बार फिर से देखिएगा सब लोग। मैंने यहाँ पे कुछ अपने साइन लैंग्वेज में भी एक स्लाइड में डाल दिया है, इसको आप देख सकते हैं कि मैंने पूरा एक पन्ने में लिखा हुआ है कि हाउ फॉक इज रनिंग, हाउ आर्टिफिशियल कॉन्टेक्स्ट इज क्रिएटेड, how AX equal to 0, copy stripe frame. I have given all these thing in my own sign language, but I have included these in your slides so that you can have a ready reference that what is happening in FOC all the time. Any questions from anybody? I can explain everything if you have any question. Yes, Aman.
No, sir, no problem.
Huh? Understood?
No problem. Yes, sir.
No
Yes, sir.
Okay. Now I have completed one module, so please be ready for a test or a quiz anytime. Okay. So in any class, I may ask a quiz, I may conduct a quiz. Fine. And generally, when my lecture is not prepared, somehow I conduct quizzes. Okay. So that you need to be careful about. Okay. So be very vigilant about the thing. Go and see the lecture video